So I have a little bit of code here pre-written, but before we get into any particulars about any of the lines for what they are, let's just run it and let's see what it does. And so we see that when we run it, a couple of these little tables pop up here. And maybe to make these tables a little bit more intuitive, let's go down a little bit of a rabbit hole. Let's say that you're up late one night and you've been up coding for hours, and you're sort of dozing off, and you finally just fall asleep at your keyboard, and you start having this weird dream. And you dream that you're in this house and you've never been here before, and the whole thing is nearly pitch black. You can just barely make out silhouettes of things here and there. You can see a little bit up close, but it's a no go far away. And you've been wandering around and you're looking for some sort of way to light up the place because you're starting to get a little creeped out because just everything's unfamiliar. You don't know why you're here. And you get into this room, and thank God, by the doorway, there's a light switch bank, and it has 8 light switches on it. And you're up close to it, so you can sort of make out that, well, underneath the far right light switch has a fancy engraved 1 underneath. And then the next switch in has a fancy engraved 2. And the pattern sort of continues here where each next switch in also has a number, and it's twice whatever the number was before. So you have a switch 1, 2, and, well, 4, and then 8 and 16 and so forth, all the way through all of the switches. And your eyes are adjusting a little bit better now, and across the room you see some silhouettes of what could be some lamps. And you see that, well, you flip on the 1 switch, and the light that comes on, well, it's a lamp, and it has a number 1 on the lamp. And, well, there's 8 of these lamps over there, and you flip on the 32 switch, and, well, another lamp comes on, and it has a 32 on it. And so you figure that, well, there's just a 1-to-1 correspondence here. If you flip on the 64 switch, well, the 64 lamp comes on. You switch on the 8 switch, well, the 8 lamp comes on. And, you're confused about this. Why this stupid counting system? Why not just count like everybody else in the world? 1, 2, 3, 4, 5, 6, 7, 8. This doubling nonsense is a stupid way to count through objects. And you're looking around the room for the first time, trying to gain some familiarity with the place. You don't recognize anything, and that thought of this counting system is sort of resonating in your head, and it starts to kind of dawn on you that, wait a second, maybe, just maybe, this is an ingenious counting system. So you really start to think about it now. It's got a hold of you, and you're thinking, well, hang on a second. What if all of the lights were off? That's what these zeros stand for. The state of each of these switches. All of these light switches are off. By the 0, you can see that. Well, if all the switches are off, they're all zeros, well, maybe we call that a 0. And if we wanted to make a 1 in our counting system, well, maybe we switch on light 1. And 2, well, maybe we switch on just light 2. Well, 3, we have to get a little creative with because we don't have any 3 lamp available to us, but we can turn on lamps 2 and 1 at the same time. Just add those together because 2 plus 1 is 3, right? Well, what would we do about 4? Well, we can just turn on just the 4 lamp. And, well, 5 would be 4 and 1, and 6 would be 4 and 2, and 7 would be 4 and 2 because that's 6, and then just we'll add 1 to that. So all 3 of these, 4, 2, and 1, would just be 7. And then, well, 8 has its own lamp, so we just turn on the 8 lamp. And 9 would be 8 and 1, and 10 would be 8 and 2, and 11 would be 8, 2, and 1. And this pattern goes to infinity. And so you get excited because you realize that, well, we can count to infinity with just 8 lamps. Well, don't get too excited because, well, you can't count to infinity with just 8 lamps. The biggest number that you can make is if all of the lamps were on. And if all of them were on, well, that would be 128 plus 64 plus 32 and so forth and so forth. And that number would be 255. But that's still pretty cool. With 8 lamps, instead of having a numbering system that maybe goes from 0, if none of the lamps are on, and then each one having its own number, 1, 2, 3, 4, 5, 6, 7, instead of going from 0 to 7, well, maybe well, I guess technically we would go to 8 there. Instead of going from 0 to 8 and having 9 numbers, we have this counting system with these lamps that, well, we can have 256 numbers. We can go from 0 to 255. Well, could this be better? Can we get more? Well, no, we can't get more, but can we make it different somehow? Can we, I don't know, maybe include negative numbers? Well, sure. As it turns out, you can include negative numbers, well, by maybe if we take this 128 lamp and we repurpose it. Maybe we turn this lamp off, and then that would represent a positive number, and then whatever number needs to be represented can be represented by the rest of the lights. Well, if we add up this 64, 32, 16, and so forth, we see that we can go up to a positive if the first light was off, making it a positive representation. We can go all the way up to 127 if we added all these together. But if this was on, making it a negative representation, well, now we can go down to negative 127. So instead of from 0 to 255, we can go from negative 127 all the way up to positive 127. But there's a little weirdness with this. If we have this first light off and all of these are zeros, well, then we have a positive 0. And if this first light is on and all of these are zeros, well, we have a negative 0. What is that? There's no such thing as a positive and negative 0. That doesn't make a whole lot of sense here. Okay, maybe we can figure out something else about that later on, but for now we have a pretty decent system. Can we count higher than 255? Well, sure. As it turns out, if you added, say, another bank of 8 light switches to this and kept the pattern extending on down, and what I mean by that is, well, the first light switch on the next bank would have to be whatever 128 times 2 is, just following this doubling pattern here. And so 128 times 2 is 256, and so that first switch would have to be 256, and then a 512, and then a 1024, and then a 2048, and a 4096, and an 8192, and then 16,000 and some change, and then 32,000 and some change. And then if you added all of those numbers up, say all the lights were on, all 16 lights were on, you added all those numbers up because you get a 32,000 plus 16,000 plus 8,000 plus 4,000 plus all the numbers after it. As it turns out, you get up to 65,535. That's crazy. We went from 0 to 255 just off of 8 switches. And we added 8 more, and we can count to tens of thousands now. That's a lot of bang for your buck. And then there's ways that we can count negative numbers here by using this first bit, but we have this weird issue here with a negative or a positive 0. Well, let's snap out of the dream for a second and kind of correlate this to real life. What does this have to do with anything, this whole trip down the rabbit hole that we just took? Well, as it turns out, your computer is just a fancy piece of electronics, and electronics are just things that manipulate electricity to do work. And the easiest manipulation of electricity that you can do is, well, to turn a switch on or off. And so you see that this in real life is real similar to how it is that numbers are stored in electronics. And if you want to have a big old number, then you need to have more electronics because, well, if you have just a little bit of electronics, like if you only had 8 switches, you can only count up to 255. And if you needed to count up to 10,000 or something, well, you need to add some switches. So when you're dealing with big values, you need to have more memory, more capabilities of doing calculations, more electronics, more hardware, essentially. And so there's a theoretical limit of infinity that you can count to with a computer. But the realistic limit is, well, it's dependent on the computer's architecture. And so what I described here, this is binary, of course. Everybody knows what zeros and ones are in computers. Even if you don't know anything about computers, everybody knows what binary is. The system for counting that I described that has the negative zero and a positive zero, that's something called ones complement. And we've fixed that problem with the negative zero and the positive zero. And we do something called twos complement now. That's beyond the scope of this video, but I encourage you to look it up now that you understand how counting is done in computers, how number storage is done in computers, and how ones complement works. Well, twos complement is the next step in that problem, and twos complement was developed to fix that negative zero problem. And so all of this follows real life things that early computer scientists had to figure out when storing data into their simple electronics of the day. And so all of this is relevant to us today, not just as a behind the scenes of how your computer works, but as it turns out, there's a lot of different data types that you can code with in C++. There's 8 different integers alone, just on the integer data type. There's 8 of them, right? And so that's what this table is. And really, I say there's 8, but there's 4. There's 2 flavors of each of the 4, essentially. You have whatever the type is, and then you have this unsigned version of that type. And then you have whatever that type is again, and then an unsigned version of that type. So really you have 4, and then there's an unsigned version. And so the regular flavor of whatever version it is, well, that's the system that we came up with down here, where we counted from negative 127 all the way up to positive 127. When we figured out how to do negative numbers, that's what the regular version is. Like, for instance, if you were to look at a short int, which is a type of integer, it requires 2 bytes in your hardware to manage that integer. And the smallest value that you can make, instead of being negative 127 and positive 127 like we figured out in our example before, the smallest value it can make is negative 32,000 and some change. And the largest value, well, just the positive 32,000 and some change. And then the unsigned short int, as opposed to the short int, well, that's more akin to this 0 to 255 stuff that we started off with originally. The unsigned also requires 2 bytes of hardware to work with that number, but it starts at 0 this time and goes up to a positive 65,000 and some change. And then as you work your way down the list to the ints, to the long ints, to the long ints, there's a tendency for them to use more and more memory, more and more hardware, but there's also a tendency for these numbers that they can deal with to get bigger and bigger. And so if you were dealing with an integer in your program, you would select the one that suited your needs. Say, for instance, you were programming a clock on a microwave. Well, that has next to no hardware that runs it. It's usually a very simple piece of electronics that runs that. And so you might want to deal with a short int here. It requires next to no hardware, and you don't need that numbers that big for a microwave clock. On the other hand, if you're dealing with some sort of supercomputer and memory is no issue, and your supercomputer task is to follow molecules around a mixture and to count, I don't know, reactions in a blah, 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 well, you might want to deal with some astronomical numbers here, and memory is no issue. So yeah, go ahead and use an unsigned long int for that. Whatever. Now, the deal with the unsigns is that, well, obviously if it starts off at 0, you can't have any negative values, so also factor that into your decisions. But as you go up this list here from short to int to long int, that's just the tendency, and then you just have the unsigned versions of each of these. Now, the other thing that I want to bring up is that this table here that I've printed out is specific to my particular computer. And if you were to print up this same table, run this same code on your computer, you may get different numbers. You may get the same numbers, but you may get different numbers here. And I'll show you how to get the numbers for your particular system. So let's go to the code first of all. I'm going to shut this down. Let's go back to the code first of all. And so if I want to find out the size of in bytes, like when we did this table and we had this column that had all the bytes that it took to for using these different types of integers. If I wanted that number, the size in bytes, in other words, that each data type takes, you just use this size of function, and it's as easy as, well, just printing out a data type. You just, like, I don't know, see out to the screen, and then you say size of, and then put a set of parentheses afterwards, and then inside those parentheses, you can do this on your own machine to find out how many bytes it takes on your computer, because once again, it may be different. And if you wanted to see the size of an integer, for instance, well, there you go. You just do it like that, and then drop down a line. And then this works for any of the data types. You can see here in this example, size of unsigned short int, size of unsigned long int, size of long int. I did it for all of them. Same old thing there. And so when we see the size of an integer here, we should just see a random 4 print out to the top of the thing now, because, well, in my system, an integer is 4 bytes, and there it goes. Now for these, for the minimum and maximum values of each data type, that's where this CLimits library comes in that I've included up top. Size of, you can just do right off the bat. You don't need any libraries for it. It's just included as a part of C++. Now for these keywords here, like short min, short max, unsigned short max, unsigned int max, etc., etc. You can tell what the minimum and maximum values are based off of these keywords. And you just need to know these keywords, or honestly, you can look up the CLimits library on Google, and it'll give you a list of keywords that you can use, to find out all of these. Or you can look here in this code, just pause the video and look at this code. And if you want to know an unsigned long max, well, there you go. Now, notice on all the unsigns too, that I just put 0 here, hard coded. The CLimits library doesn't even have a min for those. Notice that you have like a long min, and a long max. Well, that's because that's the signed version, and it has a negative component to it. For the unsigned, it's just known that the minimum is 0 because, well, it's unsigned. There's no sign to it. It's no negative sign to it. So the smallest you can go is 0 in our system, right? And the question is, how high can you go? And so they do have the max. So they have an unsigned long max or whatever, and that's the keyword for it. And you can get the keywords for all the different types here, right? And then this bottom piece, that's just what prints off our binary that we were working with at the bottom to learn about storage and all of that nonsense. And otherwise, if you want to just use any of these, remember how we created a regular variable? Like we can just say int apples, and we can just go on about our business and assign it something, and then maybe see out apples to the screen or whatever. To use any of these fancy integer types, well, you just type out the name of them. So if we wanted to have an unsigned long int, well, yeah, you just type out all of that. So you can type out unsigned long int, and then you just name it something, apples. And then now, instead of just apples equal 90, well, we can put a big old number in there because unsigned long is capable of handling it. And then we can run this program just as normal. So that's how you would use any of these things. Now, one more thing that I sort of wanted to point out, and I think that'll be it for this video actually, is let's run this again. Let's see what the max is for, say, a short int. And so the max for a short int on my system is, well, 32,000 and some change. What happens if we exceed that max? Well, let's find out. And so let's make a short int. And remember, it's 32,000 and some change. That's the max. And so we'll make this short int here, and we'll call it test. And we'll say that test is going to equal 45,000, which exceeds that 32,000 limit. And then we'll just see what test prints out to the screen. And so we can see out to the screen test, and then drop down a line. And so there should be a weird number at the top of the program now. And whatever that weird number is, well, that's going to be the result of whatever we have stored in test, which we stored 45,000, but the max is 32,000, so what happens. And so let's run this. And we see at the top that we printed off a negative 20,000 and some change. So a bunch of garbage just printed out because we've exceeded the max. That's what they call an overflow condition. When you've somehow got a value stored into a variable that the variable was not designed to handle, and it's called an overflow condition. Now on the other side, you can have what's called an underflow condition. So say that, negative 32,000 is the minimum. If we had put in negative 40,000, also garbage would have printed out because, well, negative 40,000 is smaller than negative 32,000. And so also garbage would have printed out, and that's what they call an underflow condition. Basically where you're getting garbage because you've exceeded some sort of limit. All right, so that's pretty much all I want to go over this. There's other data types that we're going to go over in general. None of them as in depth as this because, well, now you have an idea of how data is sort of stored in computers, and we can just build on that knowledge from here. So I know it was a long video, but thank you guys for being patient, and we'll see you in the next one.